Formal charges and resonance. All right, now that we know how to do Lewis electron dot structures, the last topic that goes along with those formal charges and resonances gives us the ability to distinguish between very similar forms. They both look correct, yet one is actually more correct than the other, and formal charges lets us do that. Resonance is when you can't distinguish between any differences necessarily. Well, that's not totally true. You can distinguish them perhaps, but they both look okay. They both contribute. And you'll see in a second here. Okay, so formal charges. We've got covalent compounds, right? Covalent bonds. They're sharing electrons, which means they might have partial charges. Right? They don't have full positive ones or negative ones or that kind of thing. But if we pretend that they're actually ionic, that is to say, if we pretend for a second here, theoretically, they're not sharing them, but they really do transfer electrons, perhaps, and allow them to have charges, being ionic compounds, that will give us a clue as to whether a structure is more or less correct. Right? I know that sounds like a horrible explanation. Let's just do an example, and this will be much clearer. CO2, carbon dioxide. Carbon has 4. I got 2 oxygens, 6 each, that's 12. All right, 16 electrons to work with. How should I do CO2? Well, let's see. I can do carbon, oxygen, oxygen, put it octets for everybody. How many electrons did I use? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20, I only had 16. I've got to do 2 additional bonds, like doubles and triple bonds, that kind of a thing. Well, here's one way I could do it. Let's take this lone pair on the bottom here of carbon, and then this lone pair over here from oxygen, and go ahead and make it multiple bonds. Now I'm down to 18. Got to do that once again. So again, a lone pair here from those 2 and put a multiple bond inside here. That brings me down to 16 electrons, which is correct. Now if you look at this, I've got 2, 4, 6, 8, 10, 12, 14, 16 electrons. Everything sees an octet. Looks good. Whoops, there we go. Or there's actually another way I could have done that. I could have said, hey, I've got this symmetric arrangement just like before, and then I started saying, all right, let's do the multiple bonds. So I take a lone pair off of that oxygen over here and there, and I make it a double bond. And instead of doing the same pair, let's go to the right pair this time. Lone pair off of the carbon and from this oxygen, and make that a double bond. Once again, this uses 16 electrons, so that's good. Everything has an octet. 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8 for that oxygen. Let me color those in so you can see them better. They both look good. So I've got 2 possible structures here. One of them has a single and a triple bond. The other one has 2 double bonds, yet they obey all the rules. They use the right number of electrons. Everything has an octet. Are they both correct? Maybe. Maybe they exist both ways. Maybe one way is more correct than the other, right? And how do I get at this? So this is what we use formal charges for. Formal charges are simple. You add up how much each atom owns, and you compare it to what it normally has, and see whether that atom has a formal charge or not. So, for example, look at this oxygen right here. If I look at that one, I've got how many total electrons that it owns? 5. See, it's got this lone pair, so that's 1, 2, and then it's got these shared ones. We'll just split the shared ones evenly. 1 goes to the oxygen, 1 goes to the carbon. And I've got 3 pairs, so I've got 1 from each one of those. 1, 2, 3, 4, 5. So that oxygen has 5 electrons. How many electrons does oxygen usually have? Well, it's in the 6th column over, 6 valence electrons, so it usually has 6. Now it's down to 5. It's like it lost an electron, and that would make it a +1 charge. So I'm going to write that in parentheses right above it, +1. That's its formal charge. That word formal just kind of meaning theoretical. It's not. We know it doesn't really exist that way. We're not claiming it exists that way. It's just a formal way of counting the electrons and trying to figure out who owns what. Let's look at the carbon in the middle. It's got a triple bond. Every time you have a bond, remember, it gets 1 electron from that bond because we're splitting those pairs of electrons of the bonds evenly. So the carbon has 1, 2, 3, 4. 4 electrons. Carbon usually has 4 electrons because it's in the 4th column over, so it has 0 formal charge. This oxygen over here, 1, 2, 3, 4, 5, 6, 7. It owns 7 electrons. It usually only has 6. It's like it's gained an electron, so it has a formal charge of -1. Alright, so assigning formal charges is fairly straightforward, and you get pretty good and quick at it after a while. Let's try this one over here. 1, 2, 3, 4, 5, 6 for that oxygen. Normally has 6, so that's 0. This carbon has 4. It normally has 4, so it's 0. And same thing with this oxygen. It has 6. Normally has 6. So that structure has 0 for the formal charge for every atom in it. How does that help us? Which one is more correct? Well, the rules for formal charges are twofold. Number one, the lower the formal charges, the better. Remember, we don't really have ions, right? They're sharing electrons. We have partial charges at most, okay? We don't want any one atom to own extra or too few of electrons. We don't want them to be charged, formally or not, right? If you can get to a bunch of zeros, that would be better. That basis alone looks like my right structure. This guy is more correct than the left one because it's got zeros for every formal charge, whereas, right, all these zeros, whereas this guy, +1s and -1s. The second rule of formal charges says that the more electronegative an atom is, right, that's the one that should get the negative formal charges. So, if you look at your various options out there and none of them have all zeros, let's say they all have some kind of formal charge. Well, the structure that gives the negative formal charges to the most electronegative atom, that would make sense. Right? Those electronegative atoms, they want those negative, they want the electrons, right? They hog those electrons. So if anybody gets to be a negative formal charge, the most electronegative atom should be it. So those are the two pretty simple rules on formal charges. I think quite clearly in this one we've got, here's my purple, this one with all zeros, that's going to be the correct Lewis structure for carbon dioxide, not this one. Right? It's not to say that this one never exists. It might a little bit, but it's going to be like 99% of the time like this and maybe 1% that way. I mean, this one is pretty low compared to the one with all zeros for the formal charges. All right, so let's try another one here, and this will get us to talking about resonance as well. NO2 -1. All right, nitrogen has 5. I got a couple oxygens, 6 each, 12. I got a negative charge. That's 1, 18. 18 of them. So nitrogen, set it up symmetrically. Give everything an octet. Looks like that. Count the number of electrons I've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Whoops, I only had 18, so that's okay. Take a lone pair off of adjacent ones and put a double bond in there instead. That drops me to 18. Everything has an octet. Use the right number of electrons. Looks pretty good. Alright, looks like that. But then here's the question. I've got a single bond going to one oxygen, a double bond going to the other. Is there any reason that I chose the left oxygen to be double bonded rather than the right? Is there any reason to justify that? No, there's not. Perfectly identical oxygen atoms, exactly the same kind of situation, bonded directly to that nitrogen. There's no reason I should have done that. I could have just as easily shown it this way, in other words, with my double bond going this way. Let's fill in all these lone pairs, and that works as well. Formal charges are not going to help us because it's just a different arrangement of where I put those double bonds and single bonds. And so I'll have the same set of formal charges. In other words, they're equally likely. Well, you know what? Let's go through that just to show you, just to make sure. All right. This oxygen has 6. Normally 6, so that's 0. The nitrogen, 1, 2, 3, 4, 5. It normally has 5. That's 0. This oxygen has 7. It normally has 6. That's a -1. So I got a 0, and a -1. Hey, notice that it is a -1 charge in the molecule, and the formal charges add up to -1. 0 plus 0 plus -1 is equals -1. That better be true. If it's not, you've done something wrong. Kind of a good internal check. All right, let's do formal charges over here. This one is a -1. Nitrogen is 0. Oxygen is 0. Yep. Formal charges doesn't help us to say one is better than the other. They are equally likely. So I've got two structures, both of them are equally likely. This is where I have what's called a resonance. I do a double-headed arrow to show that back and forth. We're basically saying that I've got two structures, they're both likely. I'm going to just erase these formal charges just to declutter this for a second here. Okay, draw that back in. There is my final overall answer. Then I'm going to box it like this. I've got two equally likely structures. Could go either way. If you look at my two structures, the only thing that's changing is where the electrons are. The atoms haven't moved position. It's just I've got a double on the left to the left oxygen and a single to the right oxygen over here. I've reversed that. So I've moved my electrons around, not the atoms. They're both equally correctly. Formal charges show that they're equally correct, equally likely. That's what we call resonance. Resonance structures are just where the electrons are distributed differently. And that's how I indicate it with a double-headed arrow. I got to put them both down. Okay. Now, does that mean in real life they're flip-flopping back and forth? Well, that's one way to think about it. Not a bad way. It's probably not the best way to think about it, but that's okay. You could do it that way. Another way to think about it is, keep in mind, the electrons are waves. They're just kind of smeared out high, low, right, high, low waves in different regions of space. And what this is telling me is that the actual wave, the way that these electrons are distributed, their probability is some kind of an average between these two structures. So it kind of looks like one, kind of looks like the other, but the real thing is like halfway between them. Well, let's see. A double bond here and a single bond here versus a single bond and a double. What is halfway between them? Well, it's kind of like instead of having a double and a single, you have 1 1/2 bonds between everything. Not a single, not a double, but a 1 1/2 bond. Kind of hard for us to represent that, but the electrons don't care. They're just waves. They're just smearing their probability over wherever it needs to go, right, to make the lowest energy. And that's exactly what is the best way to interpret this. Is there's 1 1/2 bond. They call it the bond order. The bond order here between those nitrogens and the oxygens are 1 1/2. A single bond would have a bond order of 1, a double bond 2, a triple bond 3. These are 1 1/2 bonds. Now, how do I get a 1 1/2? Because if you think about it, look at, I've got 3 bonds. I've got a single here, right there, and a double there. That's a grand total of 3 bonds. 3 bonds distributed amongst 2 positions, a left and a, so kind of split that up evenly. 3 half bonds in each position, or if you go to a mixed number, like in elementary school, right, that's 1 1/2. Right? So they're like 1 1/2 bonds on each spot. All right. Resonance is very important, especially when you get to organic chemistry. You're going to find that a molecule that has resonance structures has an additional stability that other ones do not have, and so very important in organic. Let's do one last example here of resonance and Lewis electron dots and all this. NCS minus. All right, here we go. Nitrogen has 5, carbon has 4, sulfur has 6. My negative charge, that's an additional 1. That adds up to 16 electrons. All right, a nitrogen, a carbon, and a sulfur. Here's one where it's not so clear which one should go in the middle. But if I look at, or if I just remember the order of electronegativity, carbon's the lowest. All right, the least electronegative goes in the middle. Don't forget that rule, right? So carbon, put a nitrogen on one side, a sulfur on the other. Everything gets an octet. Looks like that. How many electrons did I use? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons. Oops, I only had 16. All right, so I can drop that down to 18 by lone pair. Oops, I didn't hit my eraser. Lone pair, and making it a double. Or, again, another lone pair, make it a triple. Now I'm down to 16, which is correct. The whole thing has a minus charge, so there's one option. Of course, I have 2 other options. I'm going to erase this just to clean things up a little bit here. In fact, let me give myself a little more room and move this down. All right, there we go. I could have done it this way. I could have said the nitrogen with a double bond to carbon, double bond to sulfur. Looks like that. All right, so in other words, instead of doing a triple bond to the left, make a double bond and make another double bond going to the right. Again, that's 2, 4, 6, 8, 10, 12, 14, 16 electrons. Everything has an octet. That looks good. Or I could have done it with a triple bond going this way. Fill in my lone pairs. These three all are following the rules of Lewis electron dot structures. They all have octets. They use the right number of electrons. All I'm doing is moving the position of my electrons between triples and doubles and single bonds. So these are resonance structures. I'll put my double-headed arrow between them, and that is the correct structure, if you will. Oops, I didn't want to do that. Let me get that back here. Okay, there we go. Sorry about that. Just hit the wrong button. There is my overall correct structure then of that molecule. Is any one more correct? Now, see here I have a resonance structure, and they are proper resonance structures, but I'm moving electrons around to different positions as resonance structures do, but I'm moving them between different atoms. They're not all just oxygens or something like that. They're nitrogens and sulfurs. So is one of them more correct than the other? Now here's a case where I think there is going to be an answer to that. Let's go ahead and assign some formal charges here. Nitrogen, 1, 2, 3, 4, 5, so that's a 0. Carbon has a 0. Sulfur, 2, 4, 6, 7, usually a 6, so that's a -1. 0, 0, and -1. Alright, here, nitrogen has 6. Ooh, that's a -1 for nitrogen, because it usually only has 5. Carbon has 0 in this case. Sulfur, 2, 4, 6. Sulfur usually has 6, so it's a 0. Again, it better add up to be -1 each time, because this whole NCS has a charge of -1. So far, so good. Over here, nitrogen has 2, 4, 6, 7. Wow, that's like a -2. Carbon has 0. And sulfur, 1, 2, 3, 4, 5. Usually has 6, so that's a +1. Alright, so there's my formal charges. Right off the bat, I see that this one on the right is the least likely. I'll write that there. The least likely, because it's got a larger larger formal charge, that -2. With the other ones, the biggest one I see is a -1. Right? And again, if I can get down to zeros, that would be best. So the smaller the formal charge, the better. That one has a 2 in it. That's probably the least likely. Now the other two have 0, 0, and a -1. It's just, where do I put the -1? Right? Which one does it go on? Well, let's see. The nitrogen has a -1 in this case. The sulfur has a -1 in this case. Let's go check our electronegativities, which I think is, that chart is all the way up. There it is. Nitrogen electronegativity is 3, sulfur 2.5. Alright, so nitrogen is actually the more electronegative of them, which means the nitrogen should have the minus formal charge. So I look at those two. This one looks like it's the most likely, and this one is somewhere in the middle. I'll just write middle. Okay. So I've got resonant charges here. Resonance forms. They are all perfectly likely to occur, but they're not going to be 33%, 33%, 33%. It's not like that. I'm going to most of the time be sitting like my middle structure, because it's the one that satisfies the formal charges the best, right? And then this one on the right is not going to happen a whole lot because it's got that big -2 formal charge. Alright, so there you go. There are resonance and formal charges and how we can use those to show perhaps which ones are best and which ones are not. Now 7.5 we're going to skip, and the next section, 7.6, is what we'll do next.